take a journey through any modern city and you travel through the story of materials. From stone and wood to shimmering glass and steel, these are the stepping stones of our own human story. Today, materials are on the cusp of a revolution, where anything seems possible. Bionic limbs that can feel.
That was the closest thing to come to a human Terminator.
Self-repairing shoes.
Self-growing, self-reproducing even.
Mind-bending metals.
It's a bit like my parents' cat.
They can be utterly baffling.
It's like a magical world.
Or totally wondrous.
It was developed to catch stardust, so it's basically a poem. I mean, is there anything more poetic than something light to catch stardust?
And now, working with the basic building blocks of matter, scientists are blurring the lines between the living and the non-living.
We're actually making structures which nature doesn't make.
And transforming our world. The natural world is where our relationship with materials began. With stone, iron and wood, we made everything from tools to musical instruments. Gareth Ballard is a luthier, a craftsman of wooden stringed instruments, but he specialises in the ultimate in musical craftsmanship, the violin.
The violin's an amazing instrument, really. One of its features is it can sound very much like the human voice. You can really make it, scream. Or you can get real nice deep power notes. If you're a good player, that is.
Gareth is a traditional craftsman, but he embraces new technologies. Now, he's going to be taking on a new challenge. One that will really take him to the frontiers of modern science.
What I want to do is make a violin using new materials and technology.
The material he'll be using is thermoplastic polymer, and the technology is 3D printing. Can Gareth produce a beautifully sounding violin from a material that's as far away from natural wood as you can get?
To try and capture the tone, which is something that people have fallen in love with, will be very challenging.
Even more challenging because the violin will be played in 4 weeks' time to a live audience. Una Palliser has played on some of the biggest stages in the world. Her music ranges from classical and folk to gypsy.
Hi,
Una.
come in, nice to meet you.
You too.
I think when you have a really good violin, it doesn't just do what you have in your head, it also gives you inspiration and it gives you something. So it's really, it's massively a relationship between you and the instrument.
But will Una trust in Gareth's crazy scheme?
So, Una, how would you feel about testing out our 3D printed violin when
I'd
we're
love
finished?
to do it.
Do you think you would be difficult to please as a violinist?
Yeah, I do.
Great.
But can Gareth deliver a violin good enough for Una to play? Reputations are at stake.
It doesn't matter what the limitations of the instrument are, it's going to reflect on me.
It's our senses that connect us to materials and make us human. In the remote landscapes of northern Sweden, one man is crossing the boundaries between human and machine. He's been called Europe's first cyborg. In 2013, 10 years after his cancerous right arm was amputated, Magnus Niska agreed to test a revolutionary artificial hand that would be controlled by his own mind.
This arm is really amazing. I use it to everything.
With advanced materials that fuse with human tissue, the science fiction of the bionic man is becoming science fact. Magnus lives with his wife and young family in the small Swedish town of Haparanda. After struggling with a conventional prosthesis, he agreed to test one that would be bolted directly into his bone and connected to his nervous system. It transformed his life. With his prosthetic hand, Magnus controls movements with signals from his brain. If he wants to pick up a jigsaw piece, the hand responds.
With this arm I can work with almost everything. It's not feeling like a machine. It's more like my own arm. In the family life, I don't feel handicapped.
So how does this prosthetic arm work? Scientists are now learning how to interpret the signals from the brain. Electrodes implanted in Magnus's arm transmit signals from his brain to the hand, from man to machine. "50 miles away in Gothenburg, Max Ortiz Catalan is the brains behind the technology.
You have the cuff electrode that is for the nerve, and this one also has a lot of different platinum iridium contacts inside that are arranged in a special way so you get a high signal-to-noise ratio.
The implanted electrodes, unlike usual skin electrodes, live permanently within the human body and will connect directly to Magnus's nerve tissue.
You will open it and go around the nerve and place the nerve inside there, and then you will just let it coil around it. The reliability of these electrodes, or the whole system actually, is very important because these are not toys. People use these devices to assist them on their activities of the daily living. And that's why we're doing this, because we want the control to be more intuitive.
But something is still missing. A sense of touch. What if the signals could go both ways and the brain could interpret what the artificial hand touches? Researcher Loredana Zollo believes it's possible.
La nostra grande sfida è quella di poter arrivare ad impiantare una mano protesica ad un amputato e sentire l'amputato che dice "io sento che è una mia mano".
12 years ago, Dennis Sorensen lost his left hand in a firework accident. In 2013, he volunteered to take part in the pioneering Life Hand 2 experiment.
For me, it was kind of a duty when I thought this is so exciting, and I really would like to be a part of this huge project.
Dennis travelled from his home in Denmark to Rome.
Hello, Professor. Thank you.
Where he underwent a grueling 7-hour operation. 4 electrodes were implanted into his nerves, which connected to this hand via a computer interface. What happened next was remarkable.
Soft. Hot.
Amazingly, Dennis was feeling sensations from an artificial hand.
They put this round object in the life hand, and I squeezed around it, and I could immediately tell that it was round. After 10 years where you haven't had any kind of sensation of a form, then suddenly you're able to actually feel again in your lost hand. That was really incredible and something I will never forget in my life. It was really a special moment.
The Life Hand 2 experiment restored sensation that Dennis thought he'd lost forever. But unfortunately for him, the experiment was authorised only for 30 days. New materials, however amazing, need to be safe.
Che gli elettrodi sono stati testati e quindi la loro efficacia, la loro sicurezza è stata dimostrata per quel periodo. Quindi l'estensione a un periodo più lungo richiede naturalmente test di verifica di sicurezza più approfonditi.
The electrodes had to be removed, and his sense of touch in that arm was lost once more.
The fact that it was taken away again, I knew from the start, and yeah, it was just incredible, and I was very proud and also humbled to be the one who was selected for the project.
Loredana and her team continue their painstaking work. But merging man and machine brings with it new responsibilities. Is society ready to rethink what it is to be human? Our sense of touch can be the key to the sometimes baffling world of new materials. Zoe Loughlin, a curator at the Materials Library in London's University College, is an artist as well as a scientist. And her love of materials is about sensuality and fun.
You've got to kind of touch materials to really understand them. And one of my favourite to touch is this guy. Now, oh, this is quite heavy. And it looks like it wouldn't be. It's soft and it's fine, so delicate. Each one of these individual strands is like the 10th the size of a human hair. And it's incredible because this is 100% steel, but it's super, super soft, super silky. I mean, it's a bit like my parents' cat. It's kind of beautiful, elegant, steel, yarn, ball, stuff. Beautiful.
Zoe also cherishes materials because they bridge the past and the future. In amongst the synthetic skins, spacecraft soup, diamonds and socks, Zoe has a soft spot for the comedians and shapeshifters of the material world.
This really unassuming piece of wire is actually really remarkable. It tells you a lot about the crystal structure of metals, but also the relationship between materials and objects. So I put that there and grab this blowtorch. So we need a bit of heat to activate this. So turn it on, and then dun, da, 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 it transforms into a paperclip. And what's happening there is the crystal structure of the metal is realigning itself, and their crystals are returning to the place they were when they were born. So this memory, well, the memory of the metal is the memory of the crystals, and they'll realign themselves to form the shape of a paperclip.
For Zoe, materials might be magical, but she knows very well they're not magic. Their special effects are down to hard science.
It's really difficult to pick a favourite out of the thousands of materials we have, but if I'm pushed, I always come back to aerogel. Now, this is something that was donated to us by the Jet Propulsion Laboratory at NASA. And at the time they made it, it was the lightest solid in the world. So nothing was lighter than this. But it's blue for the same reasons that the sky is blue. So it's how light scatters through it, not how it absorbs and reflects certain wavelengths. So it's basically like solid sky. And it was developed to catch stardust. So it's basically a poem. I mean, is there anything more poetic than something light to catch stardust?
Capturing the light and energy of the sun has been the holy grail of scientists for centuries. In the field of modern solar energy, Professor Michael Gretzel is a renowned pioneer. But it wasn't always that way. 30 years, his colleagues thought he was crazy.
It's been a rough start and also a rough ride, especially in the beginning. People were skeptical, and we went against the prevailing opinion.
When Professor Grätzl started out, solar technology was based on silicon panels. But he had other ideas. For him, the answer was in the colours of the natural world.
I always feel very happy, surrounded by green trees in my orchard. And I love nature. I was inspired by the natural system.
Nature has its own way of converting sunlight to energy through the process of photosynthesis. Grätzl started researching how he could imitate that process to create a source of sustainable energy.
I was passionate about finding systems that would use electricity from light by not exactly imitating natural photosynthetic systems, but taking the most important cues from the photosynthetic system.
His pioneering work was based on a simple principle. The pigment that gives every plant its colour is also the chemical that converts sunlight to energy during photosynthesis. Based on these colour pigments, Grätzl created his own dyes. Today, they help make the Grätzl dye-sensitised cells, and they work like this. Dip a piece of conductive glass coated in titanium dioxide into mashed up raspberries. The resulting pink pigment makes a great anode. To create the cathode, simply scribble a layer of graphite across a second piece of glass. Add a couple of drops of iodine to complete the circuit. Expose it to light to represent the sun. Excited by the sunlight, the electrons then flow out as an electrical current. And there you have it, a fan powered by a raspberry juice solar cell. All over our cities, Grätzl saw millions of meters of glass reaching to the heavens. If all this glass were coated in transparent Grätzl cells, it could help power those buildings. But back in the early 90s, the efficiency of his solar cells was poor, and no one was prepared to back him.
Our funding dried up, and nobody believed in it anymore. But I was convinced. And sometimes a scientist has to be very persistent in his approach.
But in 1994, something happened that turned Grätzl's life and his work around.
That's when Toby came in.
I'm Toby Meyer. I am now CEO of Solarnics. Before that, I was doing my PhD work in Professor Grätzl's lab.
Ah, bonsoir, Professor.
Bonsoir.
Working side by side with Toby, Grätzl was faced with the challenge of improving the performance of the solar cells. And they still had to deal with the skepticism that often comes with the promises of new materials.
It was a total skepticism at the beginning, that this ever would be a solar cell that can be useful. People had an expectation that now this new thing will come out quickly in a very fast and elegant way. That was kind of the misconception.
So, to win people over, the partners improved the efficiency of the synthetic dye, enabling them to deliver real products.
What you see here is a table that's fit with dye solar cells and that charges a phone or any electronic device just by picking up the daylight. And when you need, you can charge up the phone with the table for free.
Grätzl's work began 40 years ago with a simple idea and a lot of ambition in his sunlit orchard. Today, the coloured windows in the Swiss Convention Centre, covered in a thin film of Grätzel cells, are a celebration of his vision and determination. And if their efficiency can be increased, as they hope, then maybe one day they'll help to power whole cities. This may be a long way off, but Grätzel will keep striving.
And you know, learning for scientists, that is the opium. It's our opium. Understanding and learning. Should never finish. So, merci beaucoup. Yes, voilà.
For traditional violin maker Gareth Ballard, his craft is a constant process of learning.
You learn from every instrument you make, so it's an ongoing development process for every maker.
But making a 3D printed violin, Gareth is on a whole new learning curve. Today he's come to Warwick University, a leading centre for 3D manufacturing. He's going to be making the most important decision in the whole process, the material that they'll use.
You can use a range of materials from polymers, plastics, metals and ceramics mainly.
Professor Greg Gibbons is a materials scientist and 3D printing expert.
Well, the way I see it, Greg, is that the sound of the violin is defined by its shape, design, and the material used. How close are we going to get?
I mean, the shape's no problem.
Yeah.
You know, we've got that. The scan is accurate, the building's accurate. Mimicking the material is going to be the really big challenge to get that to sound acoustically the same. I think a very, very big challenge.
Gareth is close to deciding on a material, but he needs a second opinion. His friend Filippo Pratani is a fellow violin maker.
These are 3 samples of the plastic that they can print with.
Right.
Which one would you rather make a violin out of?
Okay, let me feel them. I'm not sure. It's very heavy.
It sounds horrible.
It's a bit dead.
It's really dead.
This has got a nice ring, though. It's got a long ring. Between these two, I would probably pick this one. It feels the stiffer to me.
Even though Filippo chooses the same ABS polymer, Gareth is still racked with doubts.
I don't think it's ever going to be stiff enough. Just hope it doesn't collapse.
To begin the process, Gareth provides the violin to be scanned. With over 3,000 individual images, they now have the computer model that they'll be working from. And now it's time to unveil the CAD on the big screen.
We've actually got all the graining. That is the accurate graining we've managed to pick.
That is the actual grain
Yes,
of the
it
wood,
is.
is it?
It is indeed, yeah.
If you had a Stradivari, you'd be able to recreate a material that would behave a little bit like that.
You need to do a lot of physical testing of materials and a lot of physical development processes to get there, and it's certainly in the time that we've got, so there's no chance of doing that.
So, Mark, realistically, what do you think we might be able to achieve by next week?
One thing's for sure, you're giving us a real challenge in the time available, and we'll certainly do our best.
Right now, the chances of making a plastic violin that sounds good aren't looking promising. For Gareth, the sound of a violin is about the wood it's made from, and for him, it's spruce every time.
The wood plays a very important part in the construction of a violin, and this wood is very important because there's lots of long tubes going down it, which makes it very resonant.
The tubular hollows in the spruce give each of Gareth's violins their strength and flexibility.
It's a lot stiffer in its length than it is across the grain. For me, that's a very important feature because it makes the whole top plate vibrate in a very particular way, which will give accent to certain harmonics and resonances that really that is what makes the character of a sound.
So would the ABS polymer sound better if it had a similar internal structure to spruce? At this stage, the computer design can still be changed, so Gareth sends an email to Greg at Warwick.
What I suggested was to put tubes going through, you can see them here. If you imagine putting lots of straws together on a flat surface, let's say, they would be a lot stiffer on their length than they would crossways. The idea of this is not necessarily to make it resonate better, but to make it resonate more like a real wooden violin.
Gareth will find out whether his plan has worked in just 1 week's time, when the violin is played to a live audience. Just as science seems to solve our problems, so it creates them. As populations expand, so the pressure on natural resources increases, threatening the traditional way of life of many communities. Welcome to Crete. Summers here are getting longer, hotter and drier. Great for the booming tourist industry, but not so great for farmers like Nikos Epitropakis. He's worried that fresh water resources are starting to run out.
Είναι σίγουρο ότι στο μέλλον όλες οι περιοχές αντιμετωπίζουν πρόβλημα λειψιδρίας, γιατί οι ανάγκες αυξάνονται. Ουσιαστικά αυτό είναι το μέγα πρόβλημα που θα αντιμετωπίσει η επόμενη γενιά.
In the 1970s, when the island was facing catastrophic water shortages, farming was in sharp decline. To solve the problem, the government drilled deep boreholes to reach subterranean freshwater streams. Some of the water that Nikos draws from the boreholes today can be recycled, but not enough for the long term. So what happens when those streams dry up?
Το πρόβλημα που αντιμετωπίζει η περιοχή μας εδώ πέρα είναι ότι δεν υπάρχει κάποιο άλλο σχέδιο Β, ας το πούμε έτσι, που να κάνει αυτές τις εκτάσεις καλλιεργήσιμες.
Frustratingly, there's water all around the island, but one bucketful of salt water could kill the hardiest crop. But what if there was a way to desalinate, to filter out that salt?
Η θάλασσα είναι δίπλα μας και είναι μια αστήρευτη πηγή νερού. Η αφαλάτωση, αν ήταν φτηνή, με φτηνή ενέργεια και χαμηλό κόστος, θα μας έλυνε το πρόβλημα λειψιδρίας στο μέλλον.
To find a possible solution, we're going north. Denmark, a country that's not short of water. In Copenhagen, researcher Sylvie Brackvelt and her boss Klaus Nielsen are developing a revolutionary new material that could increase our freshwater supplies. Their inspiration was right under their noses, their bodies.
The whole idea came in the context of biomimicry, which basically means that you use principles from nature to apply them in industrial environment.
We're all made up of trillions of cells, and each cell wall has minuscule channels that let water into and out of the cell. These channels are made from proteins called aquaporins.
The aquaporin channels, they have been designed by nature during billions of years of evolution to filter water and only water molecules. So they're very essential for human life.
They do this by the natural process of osmosis, drawing water through the aquaporin channels into the more concentrated solution within the cell, but leaving salt ions behind. But how has the team used this natural osmotic pressure to filter water outside of the human body? Incredibly, they've developed a new material that mimics the cell wall.
So we've developed a technology to print those aquaporins embedded in a polyamide layer onto a support membrane. Right now we are producing around 1,000 meters per week.
Embedded into the surface of the material, the aquaporins only allow water molecules through. Everything else, including salt, is filtered out. But how does this material improve on existing filtering systems? A large water filtering plant works on the same principle as a coffee plunger. It's an effort for Sylvie to push even this small amount of coffee through the filter. Now imagine that scaled up millions of times.
It costs a lot of energy to push water through these filters, which means that the membranes get dirty very soon. So we need a lot of chemicals to clean them. So it's basically very expensive.
And it takes a huge toll on the environment. But the new aquaporin system is low on energy and on cost. So now Sylvie wants to test it in the real world. If the aquaporins could filter the salt from seawater, Nikos's future could look very different.
Hi.
Hi, I'm Sylvie.
Nikos.
Sylvie wants to show him, with a simple demonstration, how aquaporins could be used to water his crops. First, the raw material, seawater.
So all we need to do now is wait.
On one side, the seawater. On the other, a more concentrated liquid fertilizer. Through the process of osmosis, water will naturally be drawn, as it is in the human cell, towards the more concentrated solution. In this case, the fertilizer. If you put the aquaporin material between the two solutions, water molecules, and only water molecules, pass through to dilute the fertilizer.
Όντως, έχει παραπάνω νερό. Είναι πιο αραιωμένο.
So, water from the sea now pure enough to water Nikos's crops. But aquaporins don't just work on seawater. They can be used to filter out pollutants and contamination.
There's lots of people in the world who are lacking water, but they don't have the energy to make water. So the potential of this technology is huge.
Να έχει καλό αποτέλεσμα πάνω απ' όλα και να είναι θετικό για τον τόπο μας. Δηλαδή,
New low-energy technologies such as aquaporins will become ever more important to communities vulnerable to the threat of water shortages, providing them with a real chance of a sustainable future. Scientists who are trying to develop new sustainable materials for the fashion industry also mimic nature. These brilliant colours of the natural world have inspired the development of a unique material, and fashion designer Amy Winters has already caught on.
This type of colour is found in materials such as the morpho butterfly and beetle wings, and also fish underwater. The material actually starts to contort to your body shape, so depending on how you move, the material starts to have a completely different type of colour.
For centuries, fabrics have been coloured by chemical pigments, some highly toxic. But this extraordinary material generates its own colour from its own structure. It's called polymer opal, and it was inspired by a stone.
This is an opal that was dug out of a mine in Australia. It's iridescently coloured. You can see it has different colour play. And this has always been interested for people in the fashion industry. Part of the reason it's expensive is it's rare. So we haven't got a way of making things like this until now. So what we're interested in doing now is to make materials which show those same properties.
Studying real opals in his lab, Professor Jeremy Bornberg observed rows of evenly spaced glass spheres. He realised that the arrangement of these glass spheres was the source of the opal's changing colours.
So what's an opal? So let's imagine that we take a whole lot of oranges and we try and stack them up together. Only we haven't really got oranges, they're 1,000,000 times smaller, they're tiny, tiny spheres of glass. And what we have to do is we have to actually stack them in a perfect sequence. So if I do that with oranges, that's not so difficult. I just put them in lines like this. The way that the opal works to actually give these amazing colour effects is just because of the regularity of the stacking. So each of these spheres is about half the wavelength of a particular colour of light. And if it's transparent, the light bounces through and then bounces off the back side. But it also bounces off the top side as well. So we have all of these waves of light which are adding up with each other.
Jeremy knew that microscopic glass spheres would be impossible to manipulate accurately, so he manufactured his own plastic spheres.
We take essentially plastic bags, which are completely transparent, and we chop them up, and then we have a process where we can actually extrude them, where suddenly, when they become ordered like this, they start having a colour.
To do that, he squeezes a mass of plastic spheres into a tape.
So this is the tape we've just produced from the extruder, and now it's just a mass of nanoparticles, not in any particular arrangement. So the first thing we have to do from this is to make a film. And I can show you sort of what goes on like this. So these are our spheres. They're sort of disordered. But if I just shake them around, then what happens is they start to form a really nice lattice, just like the oranges on the stall. If we shake them in the right way, we get perfect ordering, and then we get a beautiful green or a red colour from the light scattering through this structure.
As he heats and flattens out the tape, the microscopic particles are squeezed into an ordered interlocked position. The play of light through the spheres produces the structural colour.
And in fact, we can loop it round a number of times, and when we go backwards and forwards, what we get is a film that looks something like this. So you can see it's already much greener. That's because all the spheres are now really locking into their nice positions. And that's what makes the polymer opals.
The colour of the polymer opal depends upon the spacing between the spheres.
So if you stretch them, they change colour because the spacing between the spheres changes. So this is something the fashion industry has never had. And whenever we show it to people who make clothes, they're desperate for it.
What I find particularly exciting about this type of material is not only the colour change. I mean, it's great that it can change colour, but the fact that it's so flexible and the potential it offers for the future and the design ideas which you could incorporate into this type of material are endless. It's closer to who we are as human beings, and it starts to stretch a bit like our skin. You can start to have clothing in unusual shapes, and each bend and twist of the material will create a different effect. The imagination is your limit.
With the potential to revolutionise how we produce colour in everything from banknotes to bras, Jeremy's polymer opal could make toxic chemical pigments a thing of the past. For violin maker Gareth Ballard, it's a big day. The violin he's been working on with scientists from Warwick University is about to be printed.
It's away, it's doing the first layer.
Following the digital design, the printer builds layer after layer of white ABS polymer.
So how long will it take?
Around about 24 hours or so to build this violin. So how does that compare to you making a wooden
It's a
violin?
little bit quicker than me. I mean, it'd take us about a month. It's not quite what I imagined. I feel a little bit sceptical. I think we're going to fall quite far short of sounding like a real violin.
Today, the 3D printed violin finally arrives at Gareth's workshop. Now, the moment of truth. Has his plan to improve the sound and strength of the violin worked?
So this is the moment. Wow. Feels remarkably strong, I must say. It almost feels like we've been underestimating the stiffness of this material. It doesn't feel like it's going to collapse. And the neck, what I've been worried about with this is that this would be too bendy, but I mean, the neck, it might just about manage it. It doesn't sound un-violin-like. I expected it to ring less than that. It's like a magical world. It is, it's like a snowscape. I can't quite work out what's going on. But yeah, interesting. I must say, I'm probably pleasantly surprised. I feel happier than I thought I was going to, I must say. That's the beauty of being pessimistic.
The violin, printed in a white ABS, looks promising to Gareth. But it's all about the sound. Professional violinist Una Palliser has her own concerns.
I'm a bit nervous. And in the gig, it doesn't matter what the limitations of the instrument are, it's going to reflect on me. I'm going to have to be the one who somehow pulls it off.
Hi.
Hi.
Hey.
How are you? Nice to see you.
You too.
Again.
Mwah.
I want to see inside.
What do you expect it's going to sound like?
I don't know. I think we should just open it and see. Oh! Oh my God, it's white.
Wow, gosh, it looks like wood though.
It looks like something from a museum.
It has got a funny texture on it, hasn't it?
Let me smell it.
It's having the smell test.
Wow.
Okay, ready?
Okay, drum roll, go.
It's like a viola. It kind of does pretty much what I wanted to do. I think you've done a really good job.
Wow.
Wow.
Amazing. Totally impressed.
It's way better than I was expecting. I think we can do a gig on it and it should, you know, we can play some actual tunes.
Yeah.
The violin's big test will be in front of an audience in 2 days' time. Played alongside handcrafted instruments, will it stand up to the scrutiny of a discerning audience? Cambridge, historic town of dreaming spires, academic excellence, punting on the River Cam, and jungle music.
Always carry a sound system because you never know when you're going to need to DJ. So I live in Cambridge and I'm a scientist, but for the last few years I've been running a company that I started called Novalia, and it's all about adding interactivity to print.
Novalia might look like an average print company, but there is one big difference. Their prints make a lot of noise.
So this drum poster's fun, you can touch it, it plays some beats, but we also make print that is Bluetooth and can connect through to your smartphone and then can connect onto the internet.
Using a thin layer of ink containing nanoparticles, Kate has printed electrical circuits on the paper.
This one is like a soundboard.
After giving a TED talk on nanocarbon inks, Kate demonstrated some scratch DJing on paper. Then she was contacted by a very special fan.
A year later, I got a message from probably the best scratch DJ in the world, DJ Qbert, to say, hey, seen your talk at TED. I'm bringing up my first album in 15 years, and I'd love you to make the album cover. And we want working DJ decks in the album cover. And we've partnered with the DJ app company, and it's probably been the hardest thing we've ever done.
Kate's nanocarbon inks have converted Q*bert's Humble Album sleeve into an interactive electronic conductor. Via Bluetooth, the mixer on the sleeve controls the DJ app on the phone.
When someone touches them, it's almost like they lose where they are and they get a massive smile on their face, just like they're a child. And actually, they're learning about technology without even knowing they're learning about technology. And I get massively inspired and rewarded by seeing that.
But nanocarbon inks have become more amazing since the discovery of the world's latest wonder material, graphene. Graphene is just one single carbon atom deep. Stronger than steel and transparent, a piece the size of a football pitch would weigh less than a gram.
Well, graphene is special because it has a lot of superlative properties which are much better than any other material, like strength and conductivity and flexibility and transparency and all that. But the most important thing is that it's all of these things in one material rather than a different material for each.
Graphene was first isolated at Manchester University. It may be the most advanced material in the world, but it's produced from graphite, or as most people know it, pencil lead. When graphite was first dug out of this mine near Borrowdale in the 16th century, they didn't know what to do with it, so they used it to mark sheep. Now, Manchester University researchers, chemist Sarah Vernon and physicist Nick Clark use graphite to produce graphene.
The normal sort of graphite that you dig out of a mine would look something like this. It's kind of rocky looking. But if you get really lucky and find a nice pure piece, it will have this shine to it. Now, this is nearly all carbon arranged in these two-dimensional layers held together by weak forces, which means that when you write it on paper, you can actually shear off some of the carbon layers.
We can describe the structure of graphite like a pile of paper, where it's easy to slide the sheets over each other, but they tend to clump together. But if I use a piece of sticky tape, then I'm able to pick up just one sheet.
And we can play the same trick with graphite. If I take a flake here and stick it down onto sellotape, I can then peel the rest of the flake away, leaving a thin layer of graphite behind. So this will still be quite a thick piece of graphite, but obviously if I peel it, it will become twice as thin. Split it again to make it 4 times as thin, and then 8 times as thin, and I can keep going.
And that's the key. If we do this enough times, we get down to a single layer of graphite, and that's graphene.
At Manchester, Nick and Sarah are part of a multidisciplinary team that are working hard to get graphene out into the marketplace.
We have people from physics, chemistry, material science, engineering, maths, biology. So basically pretty much every discipline, even the business school is involved in doing studies on graphene at the moment.
For all its amazing qualities, graphene isn't substantial enough to be used on its own. The Manchester team are working out ways to layer graphene into other materials to change their properties.
In terms of these layered materials, I think it's a very unique situation where you're actually making structures which nature doesn't make.
If the team can scale up the process of graphene layering, the possibilities are endless. Flexible screens, improved solar cells, DNA sequencing, and even faster electronics.
Keep a smile on your face.
The strength, conductivity, and transparency of graphene offer new possibilities to Kate. With pure pieces of graphene suspended in water, graphene ink is tough enough and transparent enough to be printed directly onto any surface with a normal printer.
The F major scale.
There's a piece of transparent plastic laid over the graphics, and on that transparent plastic, we've printed some graphene ink, and we're using graphene as a transparent conductor. So when I touch this button, it connects to my phone and makes the music play. So we've created a fun experience, but actually its purpose is to inspire. And we have no idea where this is going to go or where graphene is necessarily going to end up. More likely than not, it's going to be combined with other inventions, other pieces of technology. And it's when we combine those things together that we end up with properties, experiences, or technology that we've never dreamed could happen.
Every runner wants the ultimate trainer. So imagine this, a trainer so high-spec that it behaves like a living organism.
It just keeps growing. People would like that.
That future may not be so far away. Meet Artemis, a Persian blue cat, and his owner, researcher Dr. Martin Hanzik. Experimenting on the boundaries between the living and the non-living, his findings could revolutionize our relationship with materials. Passionately committed to preserving the natural and the built environment, he's working with a technology called protocells, artificial materials that can be made to respond like living organisms. When he's not walking in the Alps, Martin works in the beautiful historic town of Trento in northern Italy. Much as he loves them, he knows that every building here, like any structure man has ever built, is slowly deteriorating.
When we look around a city like Trento, we can see that the building materials were set there and they are slowly crumbling into their environment. And this is normal. And actually it adds to some of the romantic beauty of these kinds of ancient places. We can see various types of architecture and various types of materials that were used to build this town over the centuries. And they typically are very hard, static, unresponsive materials that one could shape to make, for example, the paving stones in the streets.
Traditional inert materials like marble or even iron and brick can't adapt to their environment. Left unprotected, they would corrode and eventually perish. To find new materials that resist the ravages of time, Martin is working with these. These unpromising-looking blobs of red oil are called protocells. And here at the Centre for Integrative Biology, they're the focus of Martin's groundbreaking work.
So in the laboratory, we do research about artificial life. So we're trying to make non-living chemical systems that behave like living systems. First, I will create the environment for the experiment, which is basically soapy water, nothing toxic. Normally an oil droplet, when you place it in water, doesn't do anything. It'll just sit there.
But Martin adds a simple chemical agent to the red oil, which makes it behave in a very different way.
So now I'll just introduce a small population of self-moving droplets to the system. And the droplet immediately starts to react. It's changing shape, and now it's starting to move through this little chemical environment that we've made and exploring the different parts of it. You can see there quite a bit still moving, and it looks like there's a bit of sort of pairing up and dancing in one corner here.
To compare this behaviour with normal oil, Martin then adds droplets of blue oil that aren't treated with the chemical agent.
And we can see by putting in this control droplet that it doesn't move. It's not interacting with its environment in any way. And that's how we can distinguish between the two systems.
Martin's vision is to apply the principle of these reactive materials to our homes and cities.
We are thinking ahead to new kinds of materials that one might be able to use in the built environment to make buildings, to make homes that are more responsive and more integrated into the environment.
But what if these new materials could do what the old materials cannot? What if they could be like living systems trying to maintain and preserve themselves? They would need to move to change their environment, just as the oil drop protocell does.
One of the future visions for making new materials with lifelike properties is that you would have a structure that is self-repairing, perhaps self-growing, self-reproducing even.
It may sound like sci-fi, but Martin's vision has already inspired London-born designer Shamiz Aden.
I'm a speculative designer and I was very much interested in looking at the future of footwear design and how emerging technologies could impact the way we run in the future.
Transforms resources.
I actually saw a TED talk on Martin, Dr. Martin Hanzig, and I was really excited by his body of research that he was doing on protocell technology. And just by chance, I just emailed him out and just said, would you be interested in collaborating with me as a student, interested in new materials? And we started working together on developing this concept of this pair of running trainers. They will adapt to the individuals as they're running. They'll be more in tune with the individual's foot and reconfigure and adapt depending on the pressure and the time.
The amoeba shoe is still only a concept, but the potential of protocell technology is real and present.
Now I'd like to introduce sort of a special guest, a 3D printed violin. I'm a bit nervous about playing it in a gig. Shall I show it to you? Wow! So it looks like it's been painted white, but actually it's made of plastic. And this is actually the colour that it came out. So yeah, we'll give it a go.
Don't you go. I got a space in my bed full of words unsaid. Got a bullet in my gun full of things undone.
It's been brilliant. I do feel proud of what I've done and how it's turned out. It's been a voyage of discovery. It seems like there's a lot of possibilities for it.
The story of materials begins in the natural world, a world that's given us the resources and the inspiration to enrich our human story. As new materials defy our imagination and enhance our world, so they're helping man and nature to thrive and grow.
So what we hope to create is kind of synergistic ecology between what is natural and what is artificial, to make a more harmonious type of integration of technology with society, with humans and with nature.